buffers resist changing in pH in aqueous solutions. Human blood plasma has a pH of 7.4, and any sudden change in pH of more than 0.2 could be fatal. Without the buffering systems in our blood, lungs, and kidneys, we will die, since we consume food that could easily change the pH of our blood by greater than 0.2. The following is an example of how the pH of the blood can be easily changed by just drinking a box of orange juice. So this is a problem that they have, and I'm going to read that and we'll solve it. The average human blood volume is approximately 5 liters with an average pH of 7.2. The question is, what will be the change in blood pH if someone drinks 250 milliliters of orange juice having a pH of 4? We're assuming that there's no buffer in the blood. The solution to this problem will show how 250 milliliters of orange juice can change the blood pH to such an extent that it could be fatal, assuming that the blood does not have a buffering system. So the first thing we're going to do to solve this problem is to calculate the hydrogen ion concentration of the blood. We know that the blood pH is 7.2. As such, the hydrogen ion concentration is equal to 10 to the negative pH, which is equal to 10 to the negative 7.2. And it turns out that that is the concentration of hydrogen ions in the blood. But concentration is not the same as amount. We have to change concentrations to the amount in moles. And we use this equation, that N is equal to C times V. We know what C is, and we know what V is. That's the volume of the blood. So using that formula, we get that the number of moles of hydrogen ions in the blood is equal to that value there times 5 liters. So that is the amount of hydrogen ions that are found in 5 liters of blood. The next thing we have to do is to calculate the amount of hydrogen ions that are found in 250 milliliters of orange juice. Again, we can calculate the concentration of the hydrogen ions by utilizing this expression here, which is equal to 10 to the negative pH. We know the pH is 4. It turns out to be that concentration of hydrogen ions in 250 milliliters of orange juice. The next thing we have to do is to see how that translates into number of moles. And again, we use that equation, number of moles equal to C times V. We know the concentration is this, and that is the volume in liters. 250 milliliters translate into 0.25 liters. When you do the multiplication, we have that for the number of moles of hydrogen ions in the orange juice. So assuming that that represents the blood volume, and we are now consuming that volume of orange juice. So in the end, we're assuming now that the blood volume will increase to that amount. You add initial volume to that volume, and that is a new volume. But we also have to add up the total number of moles of hydrogen ions. This is from the blood, and that is from the orange juice. So this will be the amount of hydrogen ions found in the blood after someone drank 250 milliliters of orange juice of pH 4. So the new hydrogen ions concentration will be equal to, using this formula, C will equal to N over V. We know the total amount is that, and we divide it by the new volume here, which is this. It turns out to be that concentration of hydrogen ions in the blood. Now we can find a new pH of the blood by doing a negative log of the new hydrogen ion concentration. I is equal to negative log of 4.84 times 10 to the negative 6. It turns out to be 5.3. That's the original pH of the blood, and this is the new pH. So you do a subtraction there, and it turns out to be that this is a change in pH of the blood. And you can see that is much greater than 0.2. So simply drinking a box of orange juice could cause one to die if our body did not have buffering systems to maintain a constant pH. These graphs show what will happen to the pH in water if a single drop of sodium hydroxide is added to it. In this case, the pH will skyrocket, and in this case, this pH will plummet if 1 drop of hydrochloric acid of that concentration is added to 20 milliliters of water. Components of buffers. There are 2 types of buffers. One type is made by mixing weak bases with salts of these bases. For example, this type of buffer can be formed by mixing ammonium hydroxide with a salt of ammonium hydroxide, which is ammonium chloride. Another type of buffer is made by mixing weak acids with salts of weak acids. For example, we can make a buffer by mixing ethanoic acid with a salt of ethanoic acid, such as potassium or sodium ethanoate. The important thing is to have the weak acid and the conjugate base of that weak acid along with it in solution. If you're using ethanoic acid, then the salt must be some type of ethanoate, such that we'll have the ethanoate ions along with the ethanoic acid. The next thing is we show how a buffer works to maintain constant pH. And the buffer that we were using, since we've been using ethanoic acid, will be the combination of ethanoic acid and sodium ethanoate. Recall that when ethanoic acid ionizes in water, it does that only to 1.3%. So there will be a very high concentration of the molecular ethanoic acid compared to a very minuscule amount of ethanoate and hydrogen ions in solution. However, when we dissolve sodium ethanoate in water, there's complete dissociation of the ions. So we'll have a high concentration of ethanoate ions in water. This will be a spectator ion. So if we mix equal concentrations of ethanoic acid and sodium ethanoate in solution, we have a very high concentration of the acid and a very high concentration of its conjugate base, which in this case is the ethanoate ions. Okay, and an equilibrium is established between the two. So this is what happens when a buffer that is made between ethanoic acid and sodium ethanoate, it is primed with a high concentration of molecular ethanoic acid and a high concentration of its conjugate base. So we solve this problem to explain how a buffer works. So according to this problem, we're having that concentration of acetic acid, the same as ethanoic acid, and that concentration of ethanoate ions in a 1 liter solution, and these are at equilibrium with each other. And you have to calculate any change in pH of the buffer if that amount of hydrogen ion is generated within the buffer without causing any change in volume. Someone could have been doing an experiment using this buffer, and something in the experiment could have been generating that quantity of hydrogen. So we want to calculate any change in pH that amount of hydrogen ion added to the solution would cause. So the first thing we do is to calculate the concentration of the hydrogen ions in the buffer, as that is what is going to lead us on to calculating the pH of the buffer. This is the equilibrium that exists between acetic acid, ethanoate ions, and hydrogen ions. The Ka value for ethanoic acid is 1.8 times 10 to the negative 5. Its Ka expression is the concentration of these two ions over the concentration of these molecules at equilibrium, and is written as such. We now want to make the concentration of the hydrogen ions the subject of the equation. So we leave this all by itself here. Take across the concentration of the acid and put it at the top, and bring down the concentration of the ethanoate ions at the bottom there, and it turns out to be that expression. But we know what are the concentrations of those species. That is it for the acid, and that is it for the ethanoic ions. So we substitute that into this expression, and it is equal to the Ka for the acid, which is 1.8 times 10 to the negative 5, and these are the concentrations of the acid and the ethanoic ion, and you can see that they cancel out each other like that. So the hydrogen ions concentration will be equal to that. Doing a negative log of that, we ended up with the pH of the buffer solution as being 4.7. The question was, what will be the change in pH when that amount of hydrogen is added to the buffer? When we add that amount of hydrogen to the solution, recall that ethanoic ions are strong bases, and if hydrogen ions are lurking around, they will quickly grab them to make molecules of ethanoic acid. So by placing that amount of hydrogen ions in the solution, it will allow a corresponding number of ethanoic ions to react with these to form a corresponding number of molecules of ethanoic acid. So in effect, what is happening, we are removing that quantity of ethanoic ions, and we are making a corresponding number of ethanoic acid molecules. So we go back to the expression. This is what is happening. We are removing these guys, and we are making a corresponding number of those guys. So we are removing from the bottom that quantity, and we are increasing the top by that quantity. So new concentrations will be 0.4 plus that amount and 0.4 minus 0.1. It turns out to be this. When you do the math there, we end up with a final hydrogen ion concentration as 3.0 times 10 to the negative 5 mole per liter. Doing a negative log of that, we see that the buffer has attained a new pH of 0.52. But the initial pH was 4.72. You subtract that, we can see there's a small change of only 0.2 in pH. So this is how the buffer works, and this will be the change in pH. For a quick review, we start with a buffer that has a large number of ethanoic ions and ethanoic acid molecules in equilibrium with each other. When hydrogen ions are added to the mixture, ethanoic ions, which are strong bases, quickly grab these to form ethanoic acid molecules. In so doing, the concentration of these ions decrease by a corresponding amount of H ion that is added, and that there increases by the same amount, and that's why we have these new concentrations here. Okay, we remove from the bottom and add to the top. We ended up with a final pH of 4.52, and the difference is this. Let's look at another sample problem now. We want to see how concentrations of the acid and the base in solution affects their ability to act as buffers, or what is called a buffering capacity. So they're saying instead of using these concentrations of the acid and the base, we're now using only 0.2 moles per liter of each, and we're adding the same amount of hydrogen ions. Alright, again, we calculate the initial pH. You know how to do that. This is how we calculate the initial concentration of the hydrogen ions. That's how we did here, and we'll do the same thing. We are doing the same thing here. A point to note is that as long as these concentrations are the same, you can see they cancel out, and therefore the pH will remain the same. First of all, we find the hydrogen ion concentration, and it turns out to be that. You do a negative log, and you see you end up with the original pH. So if we go back to the previous problem, the shift is going to happen in the same way. We are removing those ions and changing them to molecules. So we subtract this from the bottom and we add to the top. In this case, it was 0.4, 0.4, and we add to the top, subtract from the bottom. In this case, concentrations are less. Add 0.1 there, minus that. Now you have a new ratio of 0.3 over 0.1, and the new hydrogen ion concentration is equal to that. When you do a negative log of that, we end up with a new pH of 0.27. You can now see that there is a bigger difference in the pH here, which is equal to 0.43 compared with this one here, 0.2, when you use twice the concentration. Here we use 0.4 moles of each, and we got that change in pH. Here we are using half that concentration, and you can see that the pH rises twice that. So there's something what's called a buffer capacity. You can see that the ability of this buffer up here was more effective in preventing a change in pH than this guy here, which had less concentration of the acid and the base, and as such it wasn't able to buffer the solution as effectively as the one before. So the greater the concentration of the acid and the base in solution, the greater is its buffering capacity. This was the one with a high concentration. Let's suppose that you had this buffer in a beaker and you had a pH meter, and someone was adding drops of acid into the buffer and storing it, and you're monitoring the pH there. You will find that the pH will remain constant for a period of time as you keep adding the acid to it. This region where the pH does not change is called a buffering region. At some point the pH will start to rise, and the volume of hydrochloric acid that is added to that is a measure of what is called the buffering capacity of this particular buffer. As opposed to this other one here, where after you've added only half the amount of hydrochloric acid, you'll find that the pH will start to rise. So this one here will have less buffering capacity than that one there. And that has to do with the concentrations of these guys in solution. So the higher the concentration of the acid and the base, the greater is its buffering capacity. How does a buffer work when a base is added to it? If you have a buffer that has that concentration of acetic acid and ethanoic ions, same concentration in a liter of solution, and you add that amount of OH ions now, you want to calculate any change in pH of the solution that the addition of that will cause. Again, we're not going to go through all of that. We know how to calculate the pH of that buffer, okay? We did that before. This is the pH of the buffer. The only thing that we have to do now is to see how the addition of OH ions affects the pH. So listen to this now. When we add OH to the buffer solution, OH ions combine quickly with any hydrogen ions that are there to form molecules of water. So by doing that, the concentration of the hydrogen ions gets less, and according to Le-Chat's principle, to replace that, the equilibrium keeps shifting in that direction there until we have enough hydrogen ions to neutralize all these number of OH ions to form water. So effectively, what is happening is that that amount of acetic acid molecules will ionize to give a corresponding amount of ethanoic ions. We are decreasing this and we are increasing this. So we go back to the expression for hydrogen ion concentration. Look what is happening now. We are not shifting from bottom to top as happened here. The opposite is happening. We are removing an equal concentration of molecules and changing them into ions. So we had 0.4, we removed 0.1, and we added to the bottom. So now we have this new ratio. The hydrogen ions concentration now becomes that. Do a negative log of that, and it turns out to be that. See the difference? The difference is 0.26. One more time quickly. When you add OH ions to the buffer, they combine with hydrogen ions to form water, and to replace that, according to Le-Chat's principle, acid molecules they break up to give you these ions. So the shift happens now from top to bottom. Problem number 5. Instead of that like we did before, if you use that, concentrations of each, what will happen if you add the same amount of OH ions? Everything remains the same. We don't have to explain that again. You shift from the top to the bottom. We're removing that from the top, put it to the bottom here. Turns out that this is a new concentration for the hydrogen ions. The new pH is this. I can find that this is a change in pH. Look, we're going to compare this with the one before. See, this was a change in pH when you had twice the concentration of the acid and the base. When you have the concentration, the change in pH is twice that. Thank you for listening.